In this video, we are going to look at interaction of charge and electric field intensity. So, electric field intensity is a very powerful concept. Once we know the electric field intensity, we don't need to worry about where the electric field is coming from. So, for example, if I tell you that this is my electric field, and this intensity of this electric field is, say, 250 Newton per Coulomb. So as long as I'm given this, I need not worry about where this electric field is coming from. Maybe there is a positively charged plate here, yeah, or maybe there is some other charge configuration there. Maybe there are 5-point charges here, 1, 2, 3, 4, each of 2 microcoulomb or 5 microcoulomb or millicoulombs. So I need not worry about these charges at all. Right? I don't need to worry about that. As long as I'm given the electric field intensity, I can very comfortably ignore the charges which have produced this electric field. This is an important concept. Let me write it. Once we have electric field intensity, let me write full expression. Right? Once we have electric field intensity at any point in space, we can completely disregard the charge configuration which has produced this electric field. Right? So as long as I have this E here, I need not bother about where it's coming from. I got the value of E, and that would be enough for me. Now, if I place any charge here, suppose at this point, this is my point P, and I place a charge of, say, Q here, then because it's the electric field, because this charge in the electric field, this charge will experience some force, because that's the very definition of electric field. Some charge configuration here, positive charge plate or something, created this electric field, which means that here any charge, new charge you place here, that charge would experience some force. So if this is my electric field intensity and I place a charge of Q here, this Q will experience some force, and that force is given by Q times E. Very important formula. And we just need to keep in mind that for a positive charge, the direction of force will be same as the electric field, direction of electric field. Let me write. For positive Q, F, let me write as a vector, F and E will have same direction. And for negative Q, F and E will have opposite direction. Let's look at 2 simple examples here. I had to scroll so much here. So this is the first example. A charge of 2 millicoulomb is placed in an electric field having intensity of 120 Newton per Coulomb. So I see that E is given as 120 Newton per Coulomb, and Q is placed in this electric field. This is 2 times 10 to the power minus 3 Coulomb. So F is equals to, I can easily calculate, F is equals to Q times E, which is 2 times 10 to the power minus 3, 120. That's Q times E, and that will give me how much? 0.24 Newton. And because this 2 millicoulomb is positive charge, so I have to say, I can write the direction here in the direction of E. That's the answer there. Another example, second example, and here we are talking about a negative charge here. So electric field intensity is 200 Newton per coulomb. So E is given as 200 Newton per coulomb. Q is equals to 6 millicoulomb, which is 6 times 10 to the power minus 3 coulomb. So F we can easily calculate. F is equals to Q times E, and Q is 6 times 10 to the power minus 3 times 200, and that will be 1.2 Newton. And again, because this is a negative charge, minus this time I have placed a negative charge. The force is experienced by a negative charge here, so I can mention the direction here, opposite E. Now we already have seen, or rather I should say we are familiar with the expression for electric field intensity because of point charge, which is that's the formula that we have used in previous videos. So I'll just reproduce here. If this is a positive charge Q here, electric field intensity at a distance d from this is given as K Q over D square. Now this is the expression for electric field intensity because of a point charge. Yeah, I mean this Q is my point charge, which means it's in the form of it's very small charge. I mean this charge has a very small physical size. Another charge configuration which is very important, which you will need to know, is parallel plates, and that's what we are going to look at now. So these are parallel plates, and one of these these are made of conductors, and one side of this is positively charged and other is negatively charged. So because of these two positive plates, there will be electric field between these two plates, and electric field will be in this direction, always from positive charge towards the negative charge. All right, and now this electric field intensity between these two parallel plates can be very easily found using the formula E is equals to V over D, where V is equals to voltage difference between two plates, and D is equals to distance between two plates. Yeah, very straightforward formula. So suppose we have this this particular configuration here, and the voltage difference between them is suppose 300 volt, and the distance between two plates is say 10 centimeters. Right, so we are given V is equals to 300 volt and D is equals to 10 centimeter. Just remember that in physics all calculations we do with the distance measured in meters, so this will be 10 over 100 is equals to 0.1 meters. So this electric field intensity between these two plates E is equals to V over D. V is 300 divided by 0.1 is equals to 3000 Newton per Coulomb, or other unit which we can see from here is voltage over voltage per meter. So we can also use this unit, V over M. Now parallel plate, the electric field between parallel plates is uniform electric field. Uniform means electric field everywhere, like at this point, point A, point B, point C, point D, point E. At all these points, the electric field intensity is equal to 3000 Newton per Coulomb. It's a uniform electric field. Everywhere between the plates, the electric field is same. Now suppose just to further extend it, or rather just to give an example, just to extend the force on a charged particle in electric field, let's look at the force on an electron which is placed here in this, between these two electric plates. So this my point. So let me just say that I'm putting electron at point B. So this I place electron here, and at point B it means the electron will experience some force. So what we are trying to calculate, force on an electron placed at B in our diagram above. So we know F is equals to Q times E, where Q is the charge of electron. So Q is equals to 1.6 times 10 to the minus 19 Coulomb, and electric field intensity we just calculated here, 3000 Newton per Coulomb. So this electron, if I place electron at this point B between these two plates, the force that it will experience will be 1.6 times 10 to the minus 19 times 3000 newtons. You can just plug that in calculator and find the force that electron would experience. And because electron is negatively charged, so it will experience a force in the direction opposite to the, so direction will be opposite to the direction of E. So direction of E is from left to right in this diagram, so electron will experience a force from right to left. Or in other words, I mean, if you look at the geometry here, electron is negatively charged, this plate is plate on the left is positively charged, so electron will experience a force towards the left.